Take a look at this dark, tannic water. Paperbark trees and mangroves rising out of the coastal mud like bleached ribs. Salt-encrusted timber posts standing quietly in the tidal surge, right where they have stood for well over a century. This is the shallow estuarine reach near the mouth of the Fitzroy River in central Queensland. And if you stand on the mudflats at low tide, you will spot something that seems completely out of place in a mangrove creek. Rusted iron framing, heavy timber decking, and the sunken outlines of wooden barges settling into the silt. Most people who tow a boat down this track on a Saturday morning have no idea what they are floating over, because underneath this mud and stretching across the surrounding coastal basin sits one of the richest, most volatile, and most misunderstood resource structures in the southern hemisphere. Geological surveys estimate that the underlying sedimentary sequences hold tens of billions of tons of high-rank coal and deep gas reserves, enough energy to sustain national industrial demand for generations. Yet for decades, the true depth and structural complexity of these deep seams remained almost completely overlooked. How does a geological engine of this magnitude remain effectively invisible while thousands of people pass right over it? And why has an overlooked piece of coastal earth suddenly become a critical structural focus for the entire nation? To grasp the scale of what is happening here, you have to look beyond the immediate mangroves and map the basin itself. The geological structure beneath this region, what earth scientists designate as the deep extensions of the Bowen Basin, stretches across vast swathes of central Queensland, covering thousands of square kilometres of pastoral country, dry scrub, and coastal plain. At its peak development, individual subbasins in this system have delivered vast quantities of energy resources, ranking the region among the premier energy export provinces on Earth. Combine these deep coal seams with the dense gas-bearing shale layers locked directly beneath them, and recent resource assessments conducted by Geoscience Australia and the Geological Survey of Queensland put the total in-situ energy equivalent at a scale that rivals any major continental basin. It stands as one of the largest continuous hydrocarbon and mineral assessments ever documented by state and federal geological agencies. Yet, if you were to ask 100 people on a street in Sydney or Melbourne to name the precise geological formation beneath these coastal mudflats, almost none of them could pinpoint it. Most would name the Hunter Valley, some might point to the Pilbara or the Bowen Basin's surface open cuts. Virtually no one would identify the deep, overpressured sedimentary layers hidden directly beneath these quiet tidal creeks. That gap between the sheer volume of material locked in the earth and how little of its deep structure is recognized by the public is the entire story. To understand how this rift opened between surface reality and subterranean scale, you have to go back to a forgotten wooden punt, a shallow estuary, and a strange rising bubble that nobody could explain. In the early years of the 20th century, local pastoral workers and timber cutters operating along these tidal reaches noticed something unusual occurring in the stagnant pools at low tide. Bubbles were escaping continuously through the grey silt, rising day after day in the exact same spots. Curious, a local worker rowed out into the creek bed, held a flame above the rising water, and watched the pocket of air ignite into a sudden pale blue flare directly on the surface of the estuary. What had been encountered, without formal survey equipment, without geological mapping, and without any government agency present, was a direct surface expression of the vast, highly pressurized, deep basin gas and coal system sitting directly beneath a tidal creek that fishermen had navigated for generations. In the decades that followed, early survey parties attempted to tap these shallow anomalies using improvised rigs mounted on wooden barges, anchored directly into the mudflats because no roads existed through the coastal mangrove swamps. Early test bores struck heavy mineral deposits and rich hydrocarbon flows at shallow depths, operating entirely over water without fixed shore connections. Historians now consider these crude, barge-mounted setups among the earliest true amphibious drilling operations ever attempted in the Australian context, undertaken long before industrial offshore rigs were deployed in Bass Strait or off the northwest shelf. The nearby settlement was so completely transformed by the surrounding rushes that its original local name was gradually replaced on official survey maps by industrial designations. Between those early attempts and the mid-20th century, the surrounding district yielded millions of tons of high-grade coal and billions of cubic meters of gas. And yet, the true structural engine lay far deeper than those early hand-drilled bores could ever reach. The reason all of this material was trapped here in the first place goes back roughly 250 million years to the Permian period, when this portion of the Australian continent looked radically different. A vast, shallow shallow epicontinental sea and swamp network covered what is now central and eastern Queensland. Primitive plant life, giant club mosses, and marine organisms lived and died in these thermal basins in astounding quantities, their remains settling into waterlogged sediment layer after layer for tens of millions of years. As continental drift shifted the landmass and deep tectonic movements buried the basin under immense layers of river sediment and volcanic ash, heat and pressure slowly cooked the organic strata, transforming them into dense bituminous coal seams and trapped methane reservoirs. This basin, however, possesses a structural feature that sets it apart from almost any other geological province in the country. The most lucrative seams sit extraordinarily deep, between 3,000 and 4,000 meters underground, making them some of the deepest major energy-bearing sedimentary layers ever targeted for commercial development in Australia. That extreme depth subjects the rock to immense lithostatic pressure. Geologists classify it as a heavily overpressured reservoir, which explains why deep test wells in this zone can display such high initial pressure readings. It also meant that for almost the entire 20th century, reaching or evaluating these strata was either technically impossible or prohibitively expensive. The surface seams had been worked since the early 1900s, but the ultra-deep layers directly beneath them, holding the overwhelming majority of the energy reserve, sat completely untouched, waiting for geological concepts and drilling technologies that had not yet been invented. That technical turning point finally arrived in the late 2000s, when commercial exploration consortia, drawing on emerging deep directional drilling methods, quietly began securing resource leases across central Queensland. Geologists applied high-resolution 3D seismic profiling to look clean through the 3 kilometers of barren overburden that had blinded previous generations of prospectors. Once the initial core samples were brought to the surface and analyzed in laboratories, Earth scientists realized the sheer structural thickness of the formation they were looking at. What followed was a rapid surge in exploration activity. Within a few short years, high-capacity drilling rigs were mobilized into remote scrubland and pastoral blocks that had been quiet cattle country for over a century. Exploration expenditure surged, land values shifted overnight, and small regional townships braced for an economic expansion on a scale not seen since the original gold and coal rushes of the 19th century. Then, the exact mechanism that has halted so many resource developments across Australian history intervened. The regional market became overwhelmed by global economic shifts and rapid developments in competing basins. As global commodity prices fluctuated wildly in the 2000s, deep exploration projects, which required millions of dollars per well just to penetrate the hard overlying strata, lost their immediate economic justification. Rigs that had been drilled around the clock were laid up, test sites were capped, and corporate entities quietly let their long-term exploration permits expire. For nearly a decade, the quiet coastal flats and ironbark ridges returned to silence, their deep structural secrets mapped, confirmed, and once again locked economically underground. What ultimately reignited interest was not a new surface strike, but a fundamental transformation in Australia's energy infrastructure and global export linkages. The construction of massive multi-billion-dollar liquefied natural gas export terminals along the Queensland coast at Curtis Island created an unprecedented pull for deep basin gas. These new facilities transformed localized reserves into a commodity that could be cooled, loaded onto specialized tankers, and shipped directly to industrial markets across Asia. This deep Queensland formation sat within reachable distance of these newly constructed export pipelines, a pre-existing network traversing the scrub that could carry immense volumes straight to the coast. By the early 2020s, production and appraisal activities across the basin had climbed back toward historical highs, this time underpinned by long-term international supply contracts rather than speculative local ventures. That operational shift carried enormous weight. Australia had established itself alongside Qatar as one of the premier exporters of liquefied natural gas on Earth, with central Queensland's complex sedimentary basins providing a substantial portion of the eastern grid's underlying supply. Energy analysts now view these deep, overpressured formations as some of the most critical long-term structural reserves on the eastern seaboard. Infrastructure companies have spent recent years expanding pipeline corridors designed for a single purpose: to transport energy out of the inland ironbark forests and coastal mudflats directly to the deep-water ports line of sight to the Pacific. Major resource corporations have poured billions of dollars into reacquiring and consolidating the very permits that had been abandoned during the market downturn a decade earlier. Furthermore, state and federal geological agencies recently revised their structural assessments of the region. Updated seismic surveys published by Geoscientists Australia confirmed that the deep sedimentary layers hold far greater volumes of gas and high-rank coal than previously estimated in historical mid-century surveys. It stands as one of the most comprehensive regional reassessments ever undertaken by government geoscientists in eastern Australia. Researchers have also mapped previously unknown lateral extensions of the play running beneath coastal cover, opening up entirely new geological frontiers that are currently subject to intensive exploration. The shallow estuary near the Fitzroy mouth remains quiet today. The salt-bleached wooden posts still stand among the mangroves, more than a century after early workers rowed out onto the water and held a match over a mysterious gas seep rising from the mud. The shallow bubbles found by chance were merely the topmost edge of a vast, multi-kilometre deep geological system that today helps drive major industrial grids across the Asia-Pacific. Most people driving along the coastal highways today see only mangrove creeks, dry coastal scrub, and quiet tidal flats. They have no idea that directly beneath their feet sits a deep geological engine of staggering proportions, mapped, measured, and finally linked to a global grid that fully understands its value. To understand why an energy system of this magnitude remained hidden beneath Queensland's coastal mudflats for so long, you have to look at the continent's long structural evolution. The Australian continent is among the oldest continuously exposed landmasses on Earth. Across much of the western and central landmass, ancient cratons have remained structurally stable for over 2 billion years. But along the eastern edge, the Earth was repeatedly folded, rifted, and buried under massive inland seas. 250 million years ago, during the Permian period, the eastern margin of what is now Australia formed part of a vast tectonic sag known as the Basin. At that time, the land sat far further south than it does today, experiencing a cool, high-latitude climate. Vast peat swamps covered tens of thousands of square kilometres between mountain ranges and shallow marine inlets. Traditional owners, including the Darumbal and neighbouring First Nations groups who have maintained an unbroken connection to this country for tens of thousands of years, knew this landscape in its modern form as a dynamic, interconnected network of waterways and ecosystems. Long before colonial hydrographers arrived, oral records tracked shifting coastlines, river floods, and subtle natural gas seeps escaping from shallow rock fissures. The geological sequence that locked these resources thousands of metres underground unfolded through a precise three-stage sequence: deposition, burial, and tectonic entrapment. First came the starting condition. Over millions of years, dense forest vegetation fell into anaerobic swamp water, creating thick organic peat beds. Second came the triggering event. As continental tectonic forces squeezed the basin margin, the region subsided rapidly. Rivers washed millions of tons of fine silt and sand from surrounding highlands over the swamps, burying the organic matter under thousands of meters of sediment. Third came the ultimate consequence. Under extreme lithostatic pressure and elevated heat flows, the buried vegetation underwent thermal maturation, transforming into rich bituminous coal and volatile coal seam gas trapped deep within the tight rock matrix. When colonial surveyors mapped the region in the 19th century, they looked strictly at what was visible on the surface. Early state geologists, including figures like Robert Logan Jack, who published foundational geological maps for Queensland in the late 1800s, logged outcrop coal along exposed riverbanks. But early equipment could not penetrate deeper than a few hundred meters. What was missing was not an awareness of coal itself, but an understanding of the basin's deep geometry. Surveyors assumed the resource layers thinned out or ended abruptly at depth, a logical conclusion given the technology of their era. The official record remained blind to the ultra-deep zones until mid-20th century geophysical exploration introduced deep reflection seismic profiling. When government bodies such as the Bureau of Mineral Resources, the predecessor to Geoscience Australia, began running regional seismic lines across central Queensland in the 1960s and 1970s, the resulting profiles revealed a startling structural reality. The sedimentary strata did not pinch out. Instead, they plunged downward into deep synclines, buried beneath 3 to 4 kilometres of barren overburden. That structural depth created a unique geological paradox. The massive pressure of the overlying rock sealed the gas inside the coal seams and shale layers, creating an overpressured reservoir system. Yet that same depth made the resource completely inaccessible to conventional open-cut or underground mining methods. For decades, geological report after geological report filed in state archives noted the immense theoretical volume of gas and coal locked in these deep synclines, while simultaneously dismissing it as economically unviable. level. It was only in the 21st century that directional drilling and hydraulic fracturing technologies allowed exploration companies to tap into these deep, tight strata. When combined with modern high-resolution seismic modeling, geologists could finally target specific permeable fractures 3 kilometers beneath the surface with pinpoint precision. The sheer scale of the confirmed resource, rewritten by Geoscience Australia in recent assessments, totaling tens of trillions of cubic feet of deep gas across the broader Basin system, proved that the early mid-century estimates had barely scratched the surface. Yet as these deep reserves were finally mapped and verified, geoscientists encountered a new, unexpected physical anomaly deep inside the rock itself, one that threatened to defy standard reservoir engineering. What was this hidden physical property waiting 3 kilometers down, and why did it force engineers to completely re-evaluate how gas moves through the continent's deepest rock? The shift in understanding did not begin with a dramatic surface strike or a visual discovery. It began inside a climate-controlled core library in Brisbane, where thousands of meters of grey cylindrical rock sat stored in cardboard boxes. For decades, geologists examining physical drill core, extracted from test wells drilled across central Queensland, had recorded the rock as a dense, low-permeability mudstone. On paper, it was listed as a regional seal, a thick, non-porous barrier whose only purpose was to hold shallow oil deposits in place. That interpretation held until the late 2000s, when a small team of petroleum geophysicists, working alongside researchers from CSIRO and the Geological Survey of Queensland, began running fresh analytical techniques on old core samples. They were not looking at the rock through a standard hand lens. They were using high-resolution scanning electron microscopy and automated mineralogy systems to examine the pore structure at a scale of nanometers. What they saw shattered the established geological model. The rock was not an inert solid barrier. It was riddled with a dense, interconnected network of organic micropores, filled with free and adsorbed natural gas locked under extraordinary pressure. The rock was not sealing the gas. The rock was the gas reservoir itself. The reason nobody had seen this before was simple. Standard petrophysical testing protocols measured permeability by forcing fluid through core samples at atmospheric pressure. Under those artificial conditions, the tight clay minerals collapsed, sealing the microscopic pathways and giving a false reading of zero flow. When geophysicists adjusted their laboratory testing to recreate the true downhole conditions, simulating 3,000 meters of lithostatic overburden and temperatures exceeding 120 degrees Celsius, the rock behavior changed completely. To verify the true spatial extent of this hidden reservoir across thousands of square kilometers, geoscientists could not rely on core samples alone. They turned to airborne geophysical survey methods developed by Geoscience Australia. Low-flying survey aircraft towing sensitive magnetometers and gravity gradiometers swept across the Queensland interior in tight, systematic flight grids spaced just 200 meters apart. The aeromagnetic and gravity survey data recorded subtle variations in Earth's magnetic field and gravitational pull, mapping deep structural faults and basin basements that had remained completely invisible beneath blanket layers of surface soil and alluvial cover. Then came the definitive proof: 3D seismic reflection profiling. Exploration companies laid arrays of geophones across tens of thousands of hectares of pastoral leases, firing acoustic shockwaves deep into the earth using heavy vibe trucks. By measuring the precise millisecond arrival times of echoes bouncing back from deep strata, geophysicists constructed high-definition, three-dimensional digital cross-sections of the Earth down to depths exceeding 4,000 meters. The seismic reflection images showed that the deep formation was not only continuous across vast distances, but was structurally fractured in ways that explained the intense overpressuring observed in early test wells. To confirm the origin and maturity of the hydrocarbons trapped within these deep micropores, geochemical sampling and stable isotope analysis were performed on gas samples brought up during preliminary production tests. Isotopic signatures of carbon and hydrogen confirmed that the gas was thermogenic, generated at extreme depths under severe thermal cooking rather than shallow biogenic gas. Furthermore, radiometric zircon dating of thin volcanic ash beds, known as tonsteins, embedded directly within the coal seams, pinpointed the exact depositional age of the organic strata to 253 million years ago, with an error margin of less than 500,000 years. The old cadastral maps, historical mine plans, and shallow surface surveys filed in government archives had captured only the upper 200 meters of the continental crust. High-resolution satellite imagery and modern LiDAR scanning of the surface revealed almost no trace of the massive structural bowl lying beneath the grass and ironbark trees. The same ground that generations of graziers and surface miners had walked over was suddenly recognized as an energy-dense geological engine of global proportions. Yet, as the true scale and structural mechanics of this deep reservoir were scientifically proven, an urgent question emerged for the communities, pastoralists, and regional towns living directly above it. One that had less to do with deep geology and everything to do with the surface world. How does a regional landscape adapt when its deepest underground structures are suddenly linked to global energy markets? And what happens when the physical infrastructure built to extract it begins to intersect with daily life on country? The consequences of verifying this deep geological engine reach far beyond the technical papers published in geological journals. Today, the operational footprint across central Queensland is massive, expensive, and largely invisible to someone driving past on the Bruce Highway. Thousands of kilometres of subterranean steel pipelines now crisscross the regional shires, transferring high-pressure gas from remote wellheads to central compression plants, and ultimately down to the export jetties on the coast. Yet the primary surface concern raised by hydrologists and agricultural communities centres on water. To extract coal seam methane from deep target strata, operators must pump out substantial volumes of co-produced groundwater to relieve pressure inside the coal seams, allowing the gas to desorb and flow. This process directly intersects with the hydrogeology of the Great Artesian Basin, the primary source of fresh water for vast areas of inland eastern Australia. The Queensland Gasfields Commission and the Office of Groundwater Impact Assessment conduct continuous regional monitoring, tracking water levels across thousands of dedicated observation bores. When large resource figures are cited, the necessity for sober breakdown becomes clear. Industry assessments estimate total potential deep gas reserves across the basin system in tens of trillions of cubic feet. But breaking that figure down honestly reveals distinct operational realities. Only a fraction represents proven, economically recoverable reserves under current market pricing and technology, while the vast majority remains classified as contingent or prospective resources. To put a multi-trillion cubic foot figure in perspective, 1 trillion cubic feet of natural gas is roughly enough energy to supply the domestic power needs of a city of 2 million people for over 4 years. Stating the total figure without distinguishing between theoretical in situ resource and commercially deliverable reserve misleads the public about both timeline and yield. The economic and infrastructure realities on the ground are equally complex. Small regional councils, such as the Banana Shire and Western Downs Regional Council, have seen local roads, housing markets, and emergency services reshaped by the influx of mobile workforces and heavy logistics. Local graziers sit down with land access negotiators to sign conduct and compensation agreements, balancing cattle grazing against seismic lines, well pads, and pipeline easements. At the same time, environmental agencies such as the Department of Environment, Science and Innovation monitor the long-term integrity of surface ecosystems, fire risks near gas infrastructure, and potential fugitive emissions. CSIRO's Gas Industry Social and Environmental Research Alliance runs ongoing independent research measuring air quality, soil health, and groundwater connectivity to ensure that deep extraction does not compromise surface agricultural productivity. Beyond the regulatory frameworks and corporate balance sheets, the ongoing development raises a deeper, unresolved question about the land itself. Traditional owners continue to assert their rights and interests across native title determinations, working to protect cultural heritage sites, ancient springs, and sacred waterways from subterranean disturbance. The physical infrastructure may sit deep underground or behind fenced enclosures in the scrub, but its interaction with country is immediate and permanent. As drilling technology advances into even deeper horizons across the state, scientists and survey bodies are faced with a final, fundamental paradox. If a geological system of this scale could sit unsuspected directly beneath a populated coastal basin for over a century, what else remains unmapped in the vast sedimentary rocks of the Australian continent, and what happens when the final blank spaces are erased? The final answer to how an energy system of this magnitude remained hidden for over a century lies not in the depth of the rock, but in a single flaw in early survey methodology. For decades, early geologists assumed that if a sedimentary layer did not display strong permeability at shallow depth, it could not function as a regional hydrocarbon reservoir. That single conceptual assumption, written into standard survey handbooks and taught across Australian universities for generations, kept an entire multi-trillion cubic foot basin classified as inert caprock. The anomaly was not hidden by miles of impenetrable stone, it was hidden in plain sight by the very definitions used to read the map. What remains unresolved today is the full structural boundary of the play as it extends further west toward inland basins and deeper beneath offshore coastal margins. Geoscientists at Geoscience Australia and state geological surveys are currently using advanced deep seismic reflection lines and satellite synthetic aperture radar to evaluate how far these overpressured sequences extend under barren surface cover. Some remote extensions may never be fully mapped or developed, as environmental constraints and deep drilling economics impose hard physical limits on what can be extracted. The official map sheet gives the impression of a land fully measured, contoured, and understood. The reality beneath the topsoil is that the continent's deepest geological structures are only beginning to be seen as they truly are. Which overlooked geological feature or strange landscape anomaly in your own state or territory has always made you wonder what lies beneath it? Tell us in the comments below and consider subscribing to stay connected as